Good afternoon. Thank you for joining us here at the Johnson Space Center. We have a lot of spacewalking activity coming up very soon. So right now, we are going to start talking about these complicated spacewalks to repair an experiment on the outside of the International Space Station called the Alpha Magnetic Spectrometer. Now, there's a lot to this experiment, and there's a lot to the work that's been done to prepare for these upcoming spacewalks. So we're going to do it justice and split this briefing into two parts. This first hour will be dedicated to more of the programmatic side and the overall description of what is this alpha magnetic spectrometer. Joining us here, immediately to my right, is International Space Station Operations Integration Manager Kenny Todd. Kenny, thank you for joining us. And Ken Bollweg, who is the Project Manager for the Alpha Magnetic Spectrometer. Now, in today's briefing, we're going to be going over some of the high-level details, some of the information that's going on to what is going on aboard the International Space Station, all the activities there, and the Alpha Magnetic Spectrometer itself. At 2 p.m. Central, 3 p.m. Eastern, we'll go over some of the details of the spacewalks themselves that are set to kick off later this week. So, as usual, Kenny, Todd, I will hand it over to you for some opening comments, and then we'll go over to Ken Bollweg to go over some of the alpha magnetic spectrometer, some of the details there. Now, as usual, if you're joining us and would like to ask some questions on the phone, please remember to press *1 to make sure that we can select you for a question. And if you're joining us on social media, just use the hashtag #AskNASA. Kenny, Todd, I'll hand it over to you.
All right, thanks, Gary. And it's great to see everybody. Good afternoon. It was a great launch here in the last few days of NG-12. We're excited about it for a lot of reasons, but probably one of the most exciting parts of this mission is going to be this upcoming set of EVAs that we're going to do for the alpha magnetic spectrometer. I know I've seen a lot of articles. I know there's already been a lot of discussion about the AMS EVAs and what we're undertaking. So we're all very excited to finally stop talking about it and just start executing. So that part of it we're actually looking forward to. The crew currently has their hands on the tools and the equipment, and so they've had the opportunity to get in the Cygnus module, get the hardware out, start playing with it a little bit, and as of right now, everything is looking good for our first EVA this coming Friday. So our thinking right now is we'd like to do this whole thing in 4 EVAs. We'll see if that's the way things turn out in the end. But again, we're on track right now for the first EVA coming this Friday. With the upcoming schedule as we've currently got it laid out, we'll plan on doing the second EVA next Friday on the 22nd. And from that point forward, I met with the team this morning. We talked a little bit about that path around the end of November, going into the 1st of December timeframe. And we're staying a little bit fluid. We want to see how these first couple of EVAs go, along with some of the other science and research projects that came up with the Cygnus module, just to make sure that we can make it all flow in that latter part of November, early December timeframe. And so, again, from the standpoint of the first 2 EVAs, the 15th and the 22nd, are what we're comfortable in talking about. As far as the third EVA goes, we're probably looking somewhere around the 1st or the 2nd, but again, nothing firm on that particular EVA yet. Just waiting to get a little more details on the plan. But you know, it's a very challenging, I'll call it a challenging time frame here in the mid to late October, early December time frame, as we try to do the research, plus get the EVAs done and get ourselves in a good position to do a SpaceX launch here around the 4th of December. That'll be SpaceX 19, and that particular Dragon will get to station on the 7th of December. So again, a lot going on in this particular time frame, and we're just trying to get as much of the AMS work done as we can in this time frame, and then we'll start to make some better decisions once we get a little closer to the end of the month. As far as the rest of December goes, once we get the Dragon on board, we've got an incredible amount of research coming up with the Dragon. So at that time frame, it'll be pretty much impossible for us to do any additional AMS EVAs in that time frame, which is part of the reason we're trying to see how many we can get done before the Dragon gets there. But we'll see how all that plays out. In addition to that, you know, we're looking at potentially the first flight of the Boeing Starliner in this particular time frame towards the end of the year, and so we're not going to, you know, put that aside. We're going to keep working towards that milestone and doing the things we need to do, you know, on schedule to be able to support that as they continue to prep that vehicle. So, all in all, it's a very busy time frame. Again, very excited about the AMS EVAs. It's a project that we kicked off some 4 or so years ago, and at the time we weren't sure exactly how successful we would be, but we agreed to go off and look at it and look at the challenges associated with it, and the team just did a very methodical job at going through each one of those challenges, assessing, coming up with options. Sometimes they worked out, sometimes they didn't. They'd go back to the drawing board. So it's really been a real testament to the engineering team, Ken Bollweg and the AMS team, and the folks here in the EVA world, working together to try to figure out how to effect a repair of this particular piece of hardware that, quite frankly, was never built with EVA in mind. So anyway, I think there's probably some challenges still left out in front of us, but I'm very confident that the team we have in place is ready to meet those challenges based on all the work that's been done to date. So.
Very busy time that we have here.
Indeed.
Now, you mentioned this is a very complicated piece of equipment. So Ken Bollweg, can you take us through the alpha magnetic spectrometer, what this piece of equipment is all about?
Sure thing. Thanks, Gary. If we go to the first slide, please. Okay, so the AMS was launched in May of 2011 on Endeavour. Next slide. And it was placed on the ISS S3 truss on the outside, and it's been collecting data ever since. Next slide. So it's collected roughly 140 billion cosmic ray events in the last 8.5 years. Next. It's comprised of several detector systems. So the key thing that we're going to be working on in this EVA is the tracker. That's the heart of the experiment. So of the 300,000 channels, data channels on AMS, there's roughly 200,000 of those channels in the tracker. So that's really where we get most of the data from the experiment. That data is processed by 650 microprocessors in an experiment that weighs about 7.5 tons and is roughly 5 by 4 by 3 meters in volume. Next slide. So as I said, the heart of the experiment is the tracker. That's the part that's sort of a pinkish color in this picture right in the middle. And you can see there's several other detectors involved with this. So as a particle enters the detector, it's measured in 7 different ways going through all these different detectors. And that's why the AMS data is so unprecedented and why it's so accurate, because they measure the properties of the particles coming through in so many different ways. Next slide. So this is the system that we're going to be repairing. It's the cooling system for the tracker. So it's a 2-phase carbon dioxide pump loop. So you can see in the upper right-hand corner, there are pumps there that move the liquid CO2 around, and then it goes through a heat exchanger where it's made partially 2-phase. In other words, it's partially gas, partially liquid. So it's about 10% gas that goes into what's called the evaporators, and that's where we take the heat out of the experiment. By the time it goes through the evaporators, it comes out at maybe 40 to 50% gas, and then it goes through a series of radiators where it's cooled back down again, goes back into the pump, and recirculates constantly. So the chart that you see at the bottom, the blue line is what the temperature would be if we didn't have this cooling system. The red line is the data that we have from on orbit. You can see the variability is much, much smaller. In fact, on a daily basis, it doesn't vary more than 1 degree centigrade. Next slide. So this is what the tracker looks like. The gold coloring on the outside is an EMI, or electromagnetic interference shield, and then there's silicon wafers inside there. At the end of each one of those segments, you can see the part that goes vertical in the photo. Those are where the electronics are. That's where we're taking the heat out. Next slide. So this is what it looks like installed in the AMS experiment. Again, you can see those electronics right in the front end. And with the tiny tubes that are connected to it, that's where the CO2 goes through it. Those tubes are only 3 millimeters in diameter. Next slide. So this is the outside of the experiment. On the left side is a primary cooling loop. On the right side is a secondary, and that's where we're going to cut into AMS and get to that hardware and change out the pumps. So up at the top of the slide, you can see it shows the aft tracker radiator. That's the radiator that actually rejects the heat to space. Okay, next slide. So this is what it looks like inside the box. I'm not going to go through all the components. You can see there's a orange sphere up in the upper left-hand corner. That's where we're carrying roughly 5 kilograms of CO2, of liquid CO2. That's how we're going to recharge the system. And then there's an accumulator, electronics box, a series of valves right next to that orange sphere. But the key part of this is the pumps. So the pumps are what started failing 4 years ago. AMS was originally designed to last for 3 years. After a little more than 3 years, that we started having a problem with the pumps. So it's been up there now 8.5 years, so it's exceeded any sort of lifetime expectations. But it's the pumps that need to be replaced. So if you could cut back to the pump I have in my hand. So you can see this is what the pump looks like. It's very small. It's only about maybe 3.5 inches long by about 1.5 inches in diameter. And inside there's an impeller. This is the inlet to the pump. This is the outlet. The impeller is in this area right here. And that impeller is only about the size of a quarter. So it's very tiny, and it's spinning at about 6,000 RPMs, which moves about 2 grams per second of CO2 through the system. Okay, next slide. So this is what the hardware looks like. This is the actual flight hardware during assembly, and the pumps are in the lower right-hand corner. As you can see here, there are 4 of them, so they're there for redundancy. Now, the first pump has a large filter in front of it, so that's going to help clean up the system when we first started up, because the old pumps actually created some debris that needs to be filtered out before we continue. And then we'll just keep running the pumps in series. And this is designed to last for at least 11 years. Which is the current lifetime of the space station. Next slide. This shows the entire pump package, or the upgraded tracker thermal pump system, or UTTPS, going into a climate chamber at RWTH Aachen University in Germany. Next slide. And then this is the package that it was delivered to Wallops just before it was packed inside NG-12. And then on top of it, you can see 8 fittings. Those are the training fittings that are on orbit right now. We've already done 2 sessions with Luca and Drew, and they've already swaged 4 of these successfully. They've done a great job. IVA, in fact, Luca was still wearing the EVA gloves while he was doing it. Next slide. So now I'm going to talk a little bit about the fitting. This is called the AMS Advanced Fitting. If you could cut back to the hardware in my hand here. Okay, so the way this thing works, the crew will go out, and there's 8 of these welded to the pump package. They'll take a sleeve off it, an insulating sleeve, and then open the handles, as you see here, and then put a wrench. It's just a 7/8 wrench like you might have in your garage, and open this handle here and pull this plug. This plug is there to make sure no debris gets in the system and keeps it slightly pressurized while it's on orbit. Next thing they do is they take a tube that they've already put tape on, and it's already been cut with essentially bolt cutters to disconnect it from AMS, and then they do a clean cut on it and then straighten it, and then it's placed in the fitting, jammed in until you see the tape reaches just about the end of the fitting, and then they'll take this and they'll turn it, one complete turn. If you look here, you can see witness marks. You see a black line there on both halves of this, and for this one, we would say that's at an H3 position. Now what they'll do is they'll take this wrench and they'll turn it one complete turn until they see H3 again. Once they've reached that position, they'll close up the handle again, and this actually seals inside. There's some O-ring seals inside. Close everything up, pull the sleeve over it, and then go to the next fitting, the next fitting, the next fitting. There's a total of 8 fittings they do this to. Once that's complete, they'll let us know that we've finished the last one, and then we'll tell the AMS Payload Operation Control Center at CERN near Geneva, Switzerland, that we're ready to go. They'll send a command to open the valves inside the pump box, and that'll pressurize the whole system. And then within an hour, if everything has worked okay, they'll come back out, open this up, and if they see this, then the fitting is fine, it is sealed properly. If there's a problem with it, this little piston here will move, and you'll see this bright red band, and that says, I've got a problem. It sprung a leak. So with that, just like you would do at home, if you're working on your plumbing in your home, you'd go in, put the wrench on it again, and tighten it another 1/8 of a turn. Reset everything, and you're ready for another try. So that's how the fitting works. This fitting is based on a commercial off-the-shelf fitting. This is what it looks like with normal size, working with your bare hands in your garage, or whatever you're working on. It contains very tiny parts that you can barely see here in my fingers. That's what actually makes the seal inside this fitting. Everything else here is to make it the size that you can actually work with the very bulky EVA gloves. But we started out with this, welded it on a piece of tube, made a few other modifications, and put it inside that fitting. And that's how we accomplished the seals on all these. Now, to get to these, they have to remove some hardware. The first thing they're going to remove is what's called the debris shield, which is this piece of hardware right next to me. This is full scale. This is what the crew has been training with in a facility called Argos, the Active Response Gravity Offload System. And they've taken this off many, many times in several sessions. So it's gotten kind of beat up over the last couple of years. But this is the size of the shield that's going to be taken off on AMS, and it'll actually be discarded. They're actually going to take the shield and let it go retrograde, and it'll tumble back to Earth over a year to a year and a half or so. Once they get behind the shield, they get to what's called the VSB, or vertical support beam cover, and that's what this cover looks like here. It's a carbon fiber cover that has to be removed, and you can see there's several places where there are fasteners that it attaches. But unfortunately, the last couple fasteners down at the bottom can't be reached. They're inaccessible. So what they're going to do is, once they get all these fasteners off except for these last ones, they're actually going to break this off. So you can see this is one that's actually been broken during one of the Argos runs, and they'll snap the carbon fiber material off by working it back and forth until it breaks. Okay, next slide. So this gives an example of the testing that we do in this hardware. This fitting has gone through vibration testing, thermal testing, thermal vacuum, thermal cycle, thermal extremes. In the lower right-hand corner of this picture, you can see we've got a crew member in a spacesuit inside an airlock, actually swaging it during the thermal vacuum conditions. Basically, we test all this hardware to extremes just to make sure that once it's on orbit, we know it's going to work, even to the point where the tubing that it swages on, and this tubing where we actually do the swaging is 4 millimeter in diameter. The tubing inside on the tracker is actually 3 millimeter. You can see in the photographs that were up there, they actually got to the point where we damaged it severely. On the left side, you can see we actually hit the tubing with a small hammer to create all sorts of problems on it. And in another picture more toward the middle, you can see we actually milled a groove in it. So that's sort of the worst case of if you can seal this, you can seal anything. So that give you an idea. And all the other EVA tools that were developed for this have gone through similar testing to extremes just to make sure that they're going to work for sure once we're up there.
Wonderful. It's starting to come to light just how complicated these series of spacewalks are. Now, this is a very important piece of hardware on the International Space Station. Kenny, Todd, why is this important for the space station program to go out and fix this piece of equipment?
Well, some of the other forums I've been in, I've talked about the importance of AMS. It's one of those experiments that's kind of threatening to rewrite our physics books, and the way we think about, particle physics. And it's pretty incredible to have Dr. Ting associated with the program and really helping to, bring AMS and bring it to life for all of us. If you've never had a chance to sit through a talk with Dr. Ting, everybody should get that pleasure. He's just a mountain of knowledge, a mountain of background in this area. And so, yeah, we're really, really excited to have AMS on station, and hopefully with this set of repairs, we'll continue to collect data for years to come. And, there's scientists that are out there, or future scientists that are probably in elementary school and high school right now that hopefully will be able to take advantage of some of this data and really try to help our understanding of where we all came from, the history of our planet, the history of physics, and the origin of some of these different concepts that to us right now just seem hard to grasp. And so I think this experiment is doing a lot towards helping to get some clarity and really challenge some of the things that we've believed in all these years. And that's what we're trying to do with Station as much as we can.
That's right. So, it's a place to test all of these wonderful scientific experiments. Now, this was a great overview of what we have to look forward to in the space station program these upcoming months, and more about the alpha magnetic spectrometer itself and all of these intricate pieces that our two spacewalkers are going to have to work with. So we'll open it up for questions now. Again, if you're on the line, please press *1 so we know to call on you. We'll start here in the room. And again, if you are on social media, use the hashtag #AskNASA. Mark, we'll open it up for you if you could state your name and affiliation.
Sure. I'm Mark Carreau with Aviation Week and Space Technology, and I hope this is sort of a big picture question, but what would you like or need to see from the first spacewalk and maybe the second one to tell you to continue to proceed when you've got all these other things sort of competing for your time and focus as a program?
Well, and Ken may want to put a finer point on it. What I'm looking for is, we currently have the EVAs slotted in terms of the content per EVA. We know kind of going out the door. This is one big, long EVA project, and it's currently sliced up based on the amount of time that we can spend out the hatch. And so there's a certain amount of content. We're looking to go out there and hopefully not be surprised on this first EVA. There's a lot of intricate tools, as you've seen. Some things associated with getting this panel off. That's going to be a lot of what's going on that first EVA. And so for me, having us go out, being able to meet the timelines that we set in front of us, being able to get the content that we had identified and done in this first EVA gives me some confidence that the mock-ups that we've done here on the ground and all the training and all the tool development that we've done is really on track. And to me, that's going to will be the barometer that we'll sort of use as we step our way through this first couple of EVAs. When you get to the third EVA, that's where we really start to see the new pump getting put on and actually getting installed. And so this first couple of EVAs is a lot about getting things prepared for that operation, and again, where it's going to bring in a lot of these different tools that have been developed to capture fasteners and to be able to do some of the early on operations. And so that's what I see as sort of the measuring stick, is how are we doing relative to our plans that we went out the door with.
Wonderful, thank you. We'll move over to the phone. Bill Harwood. Bill.
Hello, guys. Can you hear Bill Harwood?
Yep, loud and clear.
Okay, thanks. Hey, for Ken Bollweg, back during some of the Hubble repair EVAs, there were several instances during those series of spacewalks that were not ever designed to be done by astronauts. How does this work compare to the Hubble challenges? Is it comparable? Is it more complex in your view for a suited EVA guy? And then you were just talking about the first two are kind of preliminary on this one. Which of these four EVAs would you consider the most challenging?
So comparing it to Hubble, the Hubble was designed to do EVAs. There were some parts that had to be developed, especially once they knew the various things that needed to be repaired. AMS was largely not designed to be done by EVA. The primary interfaces, like the attachment to the space station, the electrical connections, the grapple fixtures, those were all designed to be done serviced by EVA. But to get internal to AMS was never planned because it's so complex. As I said, it's a 300,000 channel experiment. So if you imagine how many wires there are inside this thing, if you're trying to make those with EVA connectors, all you'd have is a huge experiment of EVA connectors and not much science. So in that respect, it's actually more difficult than Hubble because it wasn't designed to get into this area. They weren't designed to have access with the suit. So when they get into the area right behind this debris shield, they're very constrained. They'll get in there with their hands, but then their head, their shoulders, the rest of the suit, the workstation, everything is interfering with what they're doing in that tiny space. So in a lot of respects, this is more difficult to do than the Hubble repairs were.
Thank you, Ken. All right, so we'll open it up for some social media questions. Again, if you want to continue to ask these questions, use the hashtag AskNASA. Leah, what do we have on social?
We have a question from Khan, who wants to know when the current pumps on the alpha magnetic spectrometer cooling system began to fail.
The first one failed in 2014, I believe it was March. And that was when we knew that we had a serious problem to deal with. And that's when we started investigating, why did this fail in this time? Now, like I said, that was actually 3 years after it was launched, or almost 3 years. So, and we had 4 pumps. So by that, we could last for, say, almost 12 years. But the problem with the signature of its failure indicated that we needed to investigate it, that the other pumps may not last as long. And sure enough, the next pump died, after like another 4 or 5 months. And they were being cycled at the time. They weren't all just being run, run one, then run the next one, run the next one. They were being cycled about every 3 or 4 months. And then one of the pumps actually ran for, the next 2.5 years or so. So it was fairly inconsistent, but we knew we had to do something about it. Especially since AMS was getting such compelling science, we knew we wanted to extend its life.
Wonderful, thanks, Ken. We'll take one more Ask NASA question.
This is from Saksham, who wants to know if you will be adding a new device to the alpha magnetic spectrometer, or if you're just giving updates and repairs.
Oh, this is a whole new device. It's not only replacing the pumps, it's replacing the accumulator, it's replacing heat exchangers, heaters, valves. That whole pump package, which is about this big by this tall, this wide, will be attached to the outside of AMS, and then via these fittings, this is how it gets connected with the fluid lines, and then there's power and data cables as well. So it's a whole new package that's designed to extend the life until the end of space station. In addition, the radiator that's on top of this will actually improve the cooling significantly because as things are in space with time, they degrade. The optical properties change, so the cooling isn't quite as efficient. This is actually going to improve it to the point where we're expecting the cooling to be even better than it was when we first started.
Wonderful. Thank you for that overview. I think we're going to wrap up unless there's any more questions in the room, on social media, or on the phone. Just remember to press that *1. We'll take one more from the room before we wrap up.
Thank you, Mark Carreau from Aviation Week and Space Technology again. I think since there's been some discussion on the spacesuit side in the last few months, including developing new suits, what have you done in regard to the spacesuits for the 2 astronauts to make sure that would not become an issue? Anything special, or have you just gone through a very rigorous maintenance ahead of all this?
Sure. From a spacesuit standpoint, we're in very good shape. Drew and Luca will be doing all of these EVAs, and we've already got their suits fitted, sized. We have good redundancy should we need it, but yeah, no issues that we see on the EVA suit front. We think we're in really good shape going out on Friday, and for the duration of this series.
Wonderful. This has been a great overview of the alpha magnetic spectrometer spacewalks that we have coming up, some of the program milestones to look forward to on the International Space Station, as well as what this alpha magnetic spectrometer is all about. Kenny, Todd, and Ken Bollweg, I'd like to thank you for your time today. Now, again, this is very complicated, as you saw from all the tools that Ken was bringing out, a series of spacewalks, so we'll dedicate an entire briefing after this one to going into the details of what's happening for those spacewalks. That'll be Tara Yoakum, Jeff Radigan, and John Malarski going over some of those details. Keep sending in those questions using the hashtag NASA, and stay tuned. We're going to take a short break to get set up for this next briefing that's going to take place at 2 p.m. Central, 3 p.m. Eastern, to go over these spacewalks and the details of them. Thank you for joining us here at the Johnson Space Center.